Hi, in this video we will be solving question number 53 from GATE 2019 chemistry paper. So the question is the following. If then an operator expression is given where capital Sx and the Sy are the spin angular momentum operators and alpha is the spin up eigenfunction, then the value of A is dash rounded up to 1 decimal place. So here an operator expression is given where Sx and the Sy are the spin angular momentum operator and alpha is the spin up wave function, and we have to find out the value of A here. Okay, so before jumping into the answer part, let's first understand some of the basics of angular momentum operator algebra. So here I will be briefly describing in terms of the orbital angular momentum. So here Lx, Ly and Lz are the three component, x component, y component and the z component of orbital angular momentum operator. So in the Cartesian space, that means in x, y, z space, the Lx is represented by this expression and Ly is represented by this and the Lz is represented by this expression. And the square of total angular momentum, which is the total angular momentum, is capital L, and the square of total angular momentum, that means L square equal to Lx square plus Ly square plus Lz square. Now in polar coordinate, that means in r, theta and phi space, the Lx, Ly and Lz are represented by this expression. Now look at the Lz part only. So it is very important. So Lz equal to h bar divided by I del phi, which is equal to minus I h bar del phi. And the total angular moment, square of total angular momentum, that means L square equal to this. Now we have seen this L square operator while solving the hydrogen atom problem in quantum mechanics. Now this is the commutation relationship between the two operators. Let's say A is an operator and B is an operator. Now the commutation relationship between these two operators is represented by third bracket A operator comma B operator. Now it is represented like this: A operator, B operator minus B operator, A operator. So the commutation relationship between the x component of angular momentum and the y component of angular momentum is equal to I h bar of z component of angular momentum. And the Ly Lz commutation relationship is similarly I h bar Lx, and Lz Lx commutation relationship equal to I h bar Ly. And the commutation relationship between the any component of angular momentum, that means it could be Lx, Ly, Lz, and with L square, that means square of total angular momentum is 0. Now the commutation relationship between the two operators is 0, means we can measure the observable corresponding these two operators simultaneously. So we can measure any component of angular momentum Lx, Ly or Lz and square of total angular momentum simultaneously. Now this is the eigenfunction of Lz operator. So Lz operator is actually eigen operator of spherical harmonics. Here Ylm is the spherical harmonics, that means the angular part of our wave function, orbital wave function. Now if we operate Lz on spherical harmonics, we get m h bar as an eigenvalue, then eigenvalue. So here m is the magnetic quantum number, and h bar is the h over 2 pi, where h is the Planck constant. Now L square operator is also an eigen operator of spherical harmonics, because if we operate L square on Ylm spherical harmonics, then we get L into L plus 1 times h bar as eigenvalue. Now the spin angular momentum operator algebra is quite similar to the orbital angular momentum operator algebra. That means, let's say Sx, Sy and Sz are three components of spin angular momentum operator. Now the commutation relationship between the Sx and Sy will be I h bar SZ operator. Now if we operate SZ, that means Z component of spin angular momentum on any spin eigenfunction, that means for electron there are two spin eigenfunction. One is let's say one is up spin eigenfunction, that's denoted by alpha, and another one is down spin eigenfunction, that's denoted by beta. Why? Because electron has spin quantum number is equal to half. So the possible values of ms, that means magnetic spin quantum number, is minus half and plus half. So that's why there are two possible values, two possible eigenfunction, spin eigenfunction for electron. One is we call it up eigenfunction alpha and down eigenfunction beta. Up eigenfunction corresponding ms value is plus half, and down eigenfunction corresponding ms value is minus half. Now if we operate SZ on alpha, then similarly similar to the orbital angular momentum operator, we get eigenvalue of ms h bar times alpha. Now for alpha, ms is plus half, so that means half h bar alpha. Similarly, if we operate SZ on beta, then we get minus half h bar beta. Okay. Now in this given question, this operator expression is given here. Now just focus on this part only, Sx Sy minus Sy Sx. So this is the commutation relationship between the Sx operator and Sy operator, which is the I h bar Sz. So let's say alpha, so this term becomes alpha I h bar Sz operator alpha. Now I h bar is constant term, so we can write in the outside. So I h bar alpha Sz operator alpha. Now just focus on this part here. Sz operator is operating on alpha, that means spin up eigenfunction, so we will get half times h bar times alpha. So I h bar alpha half times h bar times alpha. Now again the half h bar is constant, so we can write it down in the outside. I h bar times half h bar alpha alpha. Now alpha and beta, for electron case, alpha and beta are two spin eigenfunction, so they are actually orthonormalized. That means they are orthogonal to each other and they are normalized. So normalized means alpha or beta equal to 1. So this is actually Dirac bracket representation, and this is normalization condition, and orthogonal condition means alpha beta Dirac bracket equal to 0. So here it is alpha Dirac bracket, so that means it will be 1 or identity or 1. So it will be I h bar times half h bar, that means I h bar square 0.5. So in this operator we have to find out the value of a, so a is 0.5. So the value of a is 0.5. Now for further details you can visit the NPTEL lecture series on Introductory Quantum Chemistry. Instructor is Professor K.L. Sebastian from IISc Bangalore. Thank you.